Hello and welcome back to the video for lesson 4.6. This is all about modeling with exponential, logistic, and logarithmic formulas. We're going to introduce logistic, which is similar to logarithmic. But first, we're going to remind ourselves about exponential growth and decay. So on an exponential function, when your starting value is positive and a is bigger than 1, we're calling that exponential growth. And when c is positive and a is between 0 and 1, that's going to be considered exponential decay. Because remember, a is your multiplier. So if you're multiplying by something that's less than 1, but bigger than 0, your value is getting smaller and smaller. So example 1 here says radium-228 is a radioactive metal with a half-life of 6 years. Find an exponential decay model that gives the amount of radium at time t, where t is greater than 0. So the half-life means that whatever you start with, you're only going to have half of that in 6 years. So that means, let's say we start with 100 and we are going to have 50 in 6 years. That means that we divide AT divided by, let's just give an example here so you can see. So if I start with 100, I'm going to have 50 in 6 years. That's what this tells us. So it doesn't matter what you start with, and you're going to end with half. And we have to isolate this E. So we're going to divide by 100. So that's how you're going to get to 0.5 or 1/2. And so we want to know what this K factor is. So taking the natural log of both sides cancels the E and we get 6 times K on the right. And so if we divide by 6, we'll find K. So this model is going to be that. We're going to do another half-life problem. So it says the half-life of plutonium-238 is 88 years, given an amount, A sub 0 in grams, at time t equals 0. Find a model that describes this. So the half-life meaning this is going to be 0.5, is 88, and taking the natural log of both sides and dividing by 88, we know what K is. And so we then can use this model here. And we got 0.5. Yeah, I didn't write that, very neat. A0 E, and then this is a natural log of 1/2 over 88 times t. And so it says calculate the required time to get to 1/3. of A0. So 1/3 instead of 1/2. We're gonna have to take the natural log of both sides, so 1 natural log of 1/3, and it cancels out the E, and then we have the natural log of 1/2 over 88 times T. And we're gonna multiply by the reciprocal to isolate T. So over here, we're gonna multiply by the reciprocal as well. It's a big fraction. I didn't really need that. Let's put this into Desmos here. So we have 88, the natural log of 0.5 divided by, no, okay. The natural log of 0.5 is in the denominator. This is actually 1/3. Okay, so it's going to take us about 139.5 years. Well, a long time to get down to only 1/3. So it takes a long time to decay. She asked me that for the second little video to this last section of chapter 4.